Lesson 1-3. Solve linear systems in 3 variables. So far, we have worked with 2 variables and 2 dimensions, but sometimes there are more dimensions. We'll be doing 3 variables today, and that will graph a plane. Linear equation in 3 variables graphs a plane. A solution to a system in 3 variables is an ordered triple. Instead of an ordered pair, it's triple because there's 3 variables, x, y, z. So, is this a solution? Is 2, -4, 1 a solution of this? Well, how should we do it? Let's plug it in. This is x, y, and z. So, let's take our first equation, x plus 3y minus z equals -11. Let's plug in the 2 for the x, -4 for the y, and a 1 for the z. 3 times -4 is -12. So 2 minus 12 is -10, minus 1 is -11. Hey, that works. Let's try the next one. 2x plus y plus z equals 1. Let's put the 2 for the x, the -4 for the y, and the 1 for the z. 2 times 2 is 4. So 4 plus a -4 is 0, plus 1 is 1. Look at that, 1 equals 1. So let's try the last one. Plug in the 2 for the x, the -4 for the y, the 1 for the z. 5 times 2 is 10. 2 times 4 is 8. 3 times 1 is 3. 10 plus 8 is 18, plus 3 is 21. 21 does, in fact, equal 21. So, it works in all 3 equations. Is it a solution? Yes, it is a solution. So, graphically, we're not going to solve by graphing, but just so you can see, when the 3 planes intersect at a single point, there is 1 solution. But the 3 planes could intersect in a single line. That would be infinitely many solutions. Or they could all be the same plane, which would also be infinitely many solutions. But they could be like that. The 3 planes do not intersect at a single point. So that would be no solution. Or maybe like that. The 3 planes do not intersect. So that would also be no solutions. Or maybe they're all parallel. They don't intersect at all. That would also be no solutions. All right, to solve systems in 3 variables, we're going to use the elimination method. You do it like 2 variables, you're just going to do it more than once. So usually you'll combine the first and second equation to eliminate a variable. Then you'll combine the second and third equation to eliminate the same variable as before. You combine these new equations to find your 2 variables, and then you substitute those 2 variables into one of the original equations to get the third variable. If you get a false statement like 8 equals 0, there's no solution. If you get an identity like 0 equals 0, a true statement, then there's infinitely many solutions. We'll deal with that later. All right, here's our first example. Let's take the first 2 equations. So from the first 2 equations, it would be convenient to, looks like, eliminate y. If I multiply the top equation by 2 and leave the bottom equation, this middle equation alone, the second one, I'll get 6y and negative 6y. So multiplying the first one by 2, I'll have 4x, 6y, 14z, it's negative 6. Second equation, I don't need to multiply by anything. When I add those together, the y's will disappear. 4x and x is 5x. 6y and negative 6y is 0. 14z and 1z is 15z. And negative 6 and negative 4 is negative 10. Well, here we could divide them all by 5. You don't have to, but it'd be convenient to divide both sides by 5 just to make our number smaller. So it'd give me x plus 3z equals negative 2. All right, let's remember that one. Now let's take our second and third equations and let's eliminate the same variable. It has to be the same variable. So if I multiply the third equation by negative 2, I'll get negative 6y in the second and positive 6y in the third. So I'm taking these two. Second equation is that. The third equation, after I multiply it by negative 2, is that. And I add these together. So I'll have 3x. The y's will cancel out. I'll have negative 15z and negative 6. Notice here I could divide everything by 3. You don't have to, but it will make the number smaller if you can divide by the same thing to every number. So there's my second equation. Now I'm going to take these and I'm going to combine them. So it looks like I could eliminate x by multiplying one of these by a negative 1. So maybe I'll multiply that one by a negative 1. So I'm going to multiply it by a negative 1. That'll give me an x and a negative x. X plus negative x is 0. 3z and 5z is 8z. Negative 2 plus 2 is 0. Hey, look, we can solve for z. Z is 0. Does that mean there's no solution? No, that simply means z is 0. All right, let's take one of these and solve it for x. So let's take, I don't know, that one. Solve it for x. I know z is 0. So negative 5 times 0 is 0, so x is negative 2. Now let's take one of the original equations and solve it for y. Now let's just take this middle one. It could be any of them, it doesn't matter. All right, x was negative 2. Z was 0. So I have negative 2 minus 6y equals negative 4. Can add 2, so negative 6y is negative 2. Divide by negative 6. What? We're getting a fraction. Means we did it wrong, right? No, fractions are fine. Y is a third. That's okay. So our answer is x, y, z. And of course, you should check it by plugging it in. It's the right answer, though. I've done this one before. Let's try another one. Well, what shall we eliminate this time? Z? All right, we can eliminate z. So in the first two equations here, I'm going to multiply the top one by a negative 1. All right, so the first one multiplied by a negative 1 would be x minus 2i minus z equals negative 3. Second equation, I don't have to do anything to it to eliminate the z. I add these, so I'll have 3x. Wait, the y's canceled out. The z's canceled out. 2. So if I divide by 3, I'll get x is 2/3. Wow. Well, that's interesting. Let's just keep going here. Let's take these two. And let's eliminate the same thing. So let's multiply, I don't know, the second equation by a -2. If I do that, I'll have -4x minus 4y minus 2z and -10. And the bottom equation, just leaving the same. -4x plus 4x is 0. -4y plus 4y is 0. -2z plus 2z is 0. And -4. So there, you see all the variables disappeared. But that is not true. So if that is not true, it is no solution. We're done. Let's try another. All right, if I take these first two, it's convenient just to add them because the y's will disappear because I have a plus y and a minus y. So let me just copy them down. And let's add these. X and x is 2x. Y's cancel out. Z and z is 2z. 6 and 6 is 12. Notice these are all divisible by 2, so just to make life easier, I'm going to divide them all by 2. There we go. Now let's take the bottom two equations. We need to eliminate the same thing, which is also convenient because it's already a minus y and a positive y. I don't have to multiply by anything. So I'll just copy these down. So if x and 4x is 5x, negative y plus y is nothing. That's 5z and 30. Hey, these are all divisible by 5. So it'll be x plus z equals 6. Notice those are the same. So if I were to do elimination here, which at this point you probably don't need to, multiply one of them by -1, you get 0 equals 0, which is many solutions. If you get, a couple equations are exactly the same, it'll be many solutions. How do you do many solutions? Here's what we're going to do for the many solutions case. We're going to take and make a interesting statement because usually when it's many solutions, the planes are intersecting at a single line. So it's not everywhere in the equations, it's just a single line. So we have to describe that line. So we're going to do something like let z equal a. And I'm using that because there's no fractions. If there are fractions, we might make it 2a to cancel out a half or something. And then I could let this x plus z equal 6. Wait, z is a. So if I subtract the a, x would be negative a plus 6. So z is a. X is negative a plus 6. And then if I take one of the original equations, such as x plus y plus z equals 6, for x I could put negative a plus 6. Z is a. Negative a and a cancel out. So it looks like y is 0. So our answer is x, y, z. And that's our answer. See, what happens is no matter what number we plug in for a, we'll get a point along the line where the planes intersect. So if we put a 0 for a, I'll get 6, 0, 0. Well, that'll be a solution. If I put a 1 for an a, I'll get 5, 0, 1. That's also a solution. If I put a 2 for a A, I'll get 402. That's also a solution. So we put different numbers for A, we get different solutions. And that is how you describe many solutions in 3 variables. Why didn't we do that for 2 variables? Because we already did. The equations of the line was all the points on that line. So you just found points in the line, those were solutions. So if there are infinitely many solutions, you let z equals a and use the x, y, or z based on what is convenient. So you could see x is a or y is a, depending on what you solve for. Then you solve for another variable in terms of a, and then you plug both of those in to find the last variable in terms of a, and your solutions are going to have a's in them. And so no matter what number you plug in for a, you get points that are solutions. Hey, let's do a word problem. You have, let's say it's your maybe annoying little sibling. And they say, I have $1.42 in quarters, nickels, and pennies. I have twice as many nickels as quarters, but I have 14 coins. How many of each coin do I have? Yeah, okay, so let's solve that. We need to write some equations. Well, the first one would be our total money. So let's say we have Q number of quarters, and they're worth 25 cents. So 0.25 times the number of quarters. Then nickels are worth 5 cents. Call them N's. And pennies are worth 1 cent. Call them P's. That should equal 1.42. Now most people don't like the decimals, so maybe we'll just multiply everything by 100. So then we'll have 25Q plus 5N plus P equals 142. We have twice as many nickels as quarters. So our nickels are twice as many as the quarters. So nickels are 2Q. And our last equation is 14 coins in total. So Q plus N plus P is 14. So we could actually do this by substitution if we wanted to, or we could do it by elimination. Let's just try this by substitution. If N is 2Q, I can plug it in there for the N. So I'll have 25Q plus 5 times 2Q plus P. That's 10Q. And that 25 plus 10 is 35. So there's one new equation. Plug it in there. Get Q plus 2Q plus P equals 14, or 3Q plus P equals 14. So now I have two equations that are with Q and P. Hey, let's do those by elimination now, maybe. If I multiply the second one by a -1, we could eliminate P. So it'd be 32Q, no P's, and 128. So divide by the 32 to get Q, and we get 4 quarters. Now it'd be bad to get fractions of the number of quarters. So we have 4 quarters. I don't know, maybe we can use this one to get P. So I'll have 3 times Q, which is 4, plus P equals 14. So 12 plus P is 14. So it looks like we have 2 pennies. And, oh, hey, we have this one, n equals 2q, so n is 2 times 4, or n is 8. So we have 4 quarters, 8 nickels, and 2 pennies. So there, that was an interesting solving by combining substitution and elimination. And we did that because it was already conveniently set up with the n equals the 2q. If you'd like, we could have set it up in standard form, did a nice elimination problem, get the same answer.